this is the wave equation, and this is its initial value. And this is actually the D'Alembert's solution of this question. You see, actually, this is a very beautiful and charismatic solution formula, because actually it happens before you solve this PDE. Let's firstly look at it through the perspective of dimensional analysis. From this, we know that here we know that then we get that and for this, know that f equals to the u, and this is now let's see this. We know that f equals to u, so this dimensional agree actually, and since this the x and the ct actually they are dimensional they agree in the dimensional, so they can they can be added together. And for this term, since g is u over t, and the integral has no dimension, and here since c is x over t, this is t over x, and here actually is x, so this equals to u, and they are agree in the dimensional. And let's see, this is the wave equation. We can see this is x t, and x minus ct, x plus ct 0. And when we analyze the force on here, we firstly look at these two sides in these two lines. Actually is f x minus ct and f x plus ct, and this follows this, and in the center of it actually is the integral from x minus ct to x plus ct, and we integrate gx since it's the partial derivative relative to t of u, and this relevant to this term. It's just an intuitive perspective, and actually we could solve it. First, we silently look at, and one thing to need to emphasize is that c actually represents the speed. of this wave. And we just write and if this is this is the D'Alembert solution. We write U just as since based on what we have learned before, if we know, we could know it's relevant to our mid schools, high schools knowledge. And now let's see why the wave equation is like that. We now do some the deduction of the wave equation. This is U. Now let's see the T here. This is actually has a force T, and this is also force T. If we see this is theta, this is T sine theta, and let's say this is x, and this is x plus delta x. Actually, this is T sine theta plus delta t, and we know F1 equals to T sine theta plus delta t minus T sine theta. Now, based on the Newton's second law, F equals to ma. Since m equals to rho v, and here the x is very small. It's just like a line, and we just regard the just say is m equals to rho delta x, and this is like f equals to rho delta x, and a equals to partial like that, and f equals to T sine theta plus delta theta minus sine theta. And since when delta theta is very small, when theta is very small, we could write this as tangent. And actually, tangent theta is just line. This, which is the slope of the line, which is, and slope here is just a partial derivative. We just write and this actually equals to and here by the mean value theorem is just equal to And now we know here is this equals to that, and the delta x is not here, and we know that. Therefore, then we finish our proof of the wave